Okay, thank you. Okay, so we continue the discussions from yesterday. So yesterday we basically glanced through a broad spectrum of possible astrophysical sources of gravitational waves, for primarily focusing on the ground-based detectors. And as you know, the most promising ones that we know from experience also that are the coalescent compact binaries involving black holes and neutron stars. And there are, even well before the detection, even starting from the 90s or 80s, people have expected that these are likely to be the most promising sources for these interferometric detectors. And there are multiple reasons for that. One is that just from a simple binding energy calculations itself, one could know that these are extremely efficient sources of gravitational waves. And now we have much more accurate estimates of the total energy of the system, binding energy of the system, lost into gravitational waves from numerical simulations. And it could be like a few percent, something like up to 15% of the total energy of the system is lost into gravitational waves. And this also happens through a very small time scale. Most of the energy loss happens over the last few orbits during the in-spiral and during the merger of these objects. And it's interesting to get just a simple estimate of that. So for example, if you assume about 10% of the total energy of the system is lost into gravitational waves, and the time scale is about a few hundred GM by C cube. And then one could calculate the peak luminosity. And remarkably, it's independent of the mass. It's independent of the mass of the black holes because it's a reflection of the fact that general relativity has no scale. Everything is scalable. So of course, more massive systems emit larger amount of energy, but that happens through a longer time scale. And the time scales are also proportional to m. So the peak luminosity is sort of independent of the mass. And that's an extremely large number, like 10 to the 47. Much more than that, about 10 to the 53 watts or something. And that is extremely large luminosity. And this number is basically larger than the stellar luminosity of all the stars in the visible universe. So that they are extremely efficient sources of gravitational waves, which will enable us to see them at very far distances, cosmological distances. And even, the second is that we know that they exist. Now that we know they exist because they have been observed, but well before their observations, we have had many lines of evidences that these systems should exist. And the most prominent of them is the observation of double neutron stars in our galaxy that are observed as binary pulsars. This is a slightly older estimate of the mass measurements of neutron stars as binary pulsars, and we have now ordered probably over 20 such binary systems in our galaxy. And the extrapolation is that there will be thousands of such binary pulsars in our galaxy. We are only seeing a small fraction of them. And we also have, radio astronomers also have measured the change in the orbital period of these binaries due to the emission of gravitational waves. The most remarkable and the first example is the so-called Hals-Taylor binary pulsar, where people have measured the decay of the orbit over last few decades. And this change in the orbital period agrees precisely with the prediction of GR calculated using the leading order quadrupole formula. And from this, you could estimate how long it will take for these binary pulsars to merge to finally reach the frequency band of these advanced LIGO and Virgo detectors, and that takes up over 1 billion years or something. And in the last 2 decades, more relativistic systems have been observed, tighter binaries which have orbital periods of hours instead of several hours or tens of hours for the case of Hals-Taylor binary pulsars. The most remarkable one is the so-called double pulsar, where people have observed the radio pulses from both neutron stars. And these also, again, take order 100 million years to merge and reach the frequency band of LIGO. So the first, at least some of the, okay, not the first, but some of the more recent estimates of the expected detection rates for LIGO and Virgo of double neutron star mergers, one of the most reliable ones came from modeling the population of these double neutron star systems in our galaxy and combining it with various kind of selection effects and making a projection. And even before LIGO and Virgo made their first detections, it was fairly clear to astronomers and astrophysicists that we are getting to the regime of detecting these things in the next decade or so. The third aspect of the system, which makes them again promising as sources of gravitational waves, is that they are extremely simple and clean systems. This is very different from, for example, what has happened in core collapse supernovae, where a lot of multi-scale physics plays a crucial role in determining the nature of the collapse as well as the emission of gravitational waves. And here, for most part of the evolution of these binaries, you could treat these as basically point particles in basically a two-body problem in GR. They are driven by the gravitational radiation reaction and spiral inwards. Towards the end, things like the fact that these are finite-size objects, etc., would start to matter. They would introduce sort of higher-order post-Newtonian corrections to the observed gravitational wave signal, and eventually these objects could, if a neutron star, they would get tidally disrupted. These black holes, their horizons would deform in a very non-trivial way, and there could be very complicated dynamics that one has to model using numerical relativity. But still, modeling of even the exact calculations of this two-body problem is much easier than, for example, the supernova problem that one has to solve to calculate gravitational waves from these collapsing stars. So this, the fact that they are clean systems enabled us to compute very accurate models of the expected signals and use these models to search for these signals that are buried in the data. So one could use optimal techniques, and this is called match filtering, etc., which basically involves cross-correlating each data segments with theoretical models of the expected signals as predicted by GR, and if required, other aspects like hydrodynamics and nuclear physics in the case of neutron stars. If one also has made a detection, one could also infer the source properties, because there is a fairly reliable way of mapping the source properties to the signal. So one could fairly accurately calculate the imprint of the source properties in the observed gravitational wave signal, and one could kind of invert this problem, and one could get posterior distributions of the source parameters, given that we have observed a particular signal. So the rest of this talk, I will, at least this talk would have kind of two parts. One is I would give a bit more detail on the physics of the coalescence of these objects, and what are the kind of how various source properties would imprint on the observed gravitational wave signal. And the second half, I will give a broad overview of how well we have understood so far what do we know about these sources from the observations of gravitational waves over the last 10 years. So broadly speaking, this is a picture, the famous picture that Kip Thorne drawn well before the first detection. So this was the naive expectation that people had of what we would see from these coalescences of these objects. Basically, you have these two compact objects. They could be black holes or neutron stars. They would have their own spill angular momentum. They're drawn by these dragging of initial frames. And they would also have an orbital motion. They could have been formed by various astrophysical processes. We don't have a clear picture yet, but there are various astrophysical models of how such compact binaries could be formed. I briefly mentioned two of them yesterday. One is basically through the isolated evolution of a binary system of two massive stars. And the second is that they could be formed through dynamical interactions in dense environments like globular clusters and nuclear clusters, where you expect a lot of multi-body interactions. Again, these are not the only possible ways of forming these binaries. There are in the recent times, the last few decades, more and more possible formation channels have been proposed. For example, people have argued that again, the viscous environments around the galactic center, where we have a lot of gas dynamics, could also be used to reduce the orbital separation of binary systems, because as I mentioned yesterday, the conventional ideas of bringing the separation down so that the gravitational radiation can take over to spiral these black holes and merge them in the age of the universe was either conceived to be through this common envelope evolution, where the primary compact object is moving in a common envelope with the core of the secondary, or the tightening could happen through multi-body interactions. But in the galactic centers, for example, the accretion disks around of the supermassive black holes, again, one could have a viscous medium which could help to reduce separations. So there are people who have argued that these sort of accretion disks around supermassive black holes could be one possible site to form these objects as well. There are several such models proposed recently. But irrespective of that, once you form these binaries through some astrophysical mechanism, basically, if they are sufficiently close, then the gravitational radiation reaction would take over and spiral them towards each other. And eventually, they would be moving it with relativistic velocities, and these objects would merge and forming a single object. In the case of black hole, it's a common horizon, which is deformed. And these deformed objects would basically oscillate, emitting characteristic radiation modes called the quasi-normal modes, and settles into a quiescent curved black hole. In the case of objects, binaries involving neutron stars, the dynamics is much more complicated because these are finite-size objects, and during the close interaction, close in spiral, these objects could get tidally deformed. And in fact, in the final stages of the spiral, they get tightly stripped by the companion tidal field, and basically it can throw away a lot of nuclear matter. It can unbound a part of this nuclear matter, and this nuclear matter could escape the binary, and through various nuclear reaction, in particular the so-called R process, it can synthesize several heavy elements which are unstable, and their decay could produce various kinds of electromagnetic radiation called kilonovae. Also, some of this the ejected material could fall back to the newly formed black hole, and it could launch a jet, a relativistic jet, and it could produce what is called a short, hard gamma ray burst. In terms of modeling, when these objects are far apart, you can treat them as point particles with slow velocities in weak gravitational fields. So the so-called post-Newtonian approximation to general relativity, which basically involves basically expansion, like a low velocity expansion of the Einstein's field equations in terms of a small velocity parameter, v by c. And that works very well in modeling the orbits and the corresponding gravitational wave emission from the early in spiral. But eventually, when these objects would come close, they would move with velocities close to the speed of light, and these approximations would break. And one has to basically solve Einstein's equations numerically using large supercomputers. And the final part of the so-called ring down basically can be modeled by basically black hole perturbation theory, where you treat this problem as a perturbation over a background geometry of the curved black hole, and one can compute the frequencies and the damping times of the quasi-normal modes. But again, the amplitudes of these different quasi-normal modes depend on the precise nature of the perturbation, and that one needs to do numerical relativity to understand the relative amplitudes of these modes. Yeah. No, I don't think so. Yeah. And this shows an actual a gravitational waveform from the coalescence of two black holes. And as you can see, in the early part shows a what is called a characteristic chirping signal, where both the amplitude and the frequency is increasing with time. And you can basically understand this is like a runaway process. Basically, the frequency of gravitational waves is twice the frequency of the orbit and the leading, the dominant mode. And during the early periods, the orbital frequency or orbital velocity, orbital frequency is small. So if you remember, the gravitational waves have amplitude, the strain has an omega square in it because of the second time derivative of the quadrupole moment. So you have, when the frequencies are small, the gravitational wave amplitudes are also small. But eventually, because of the radiation reaction, the orbit shrinks and the frequency has to increase, which means that the gravitational wave amplitude also has to increase, which will cause a larger emission of gravitational waves and a larger amount of in spiral due to the energy loss. So basically, both the frequency and amplitude increases in a non-linear way, and eventually these objects would merge and form a common object which is deformed, and basically that object damps down into a stationary curved black hole by emitting these quasi-normal mode radiation. And this has a nature that basically it has an exponential fall off. You can see this exponential fall off, and basically a single frequency. So let me go a little bit of detail on these aspects of how one could get a sense of the dynamics and the expected gravitational waves. So this plot shows how the orbital separation is changing. Is basically the orbital track of the center of mass, the reduced mass of the system, of a binary system. You can see that at early times, basically you can approximate this. You can visually see that. Basically, you can approximate this as a sequence of circular orbit. Basically, it's an adiabatic approximation. You assume that the orbital time scale is much shorter than the in spiral time scale. Basically, the change in the orbital period happens much slower than the orbital period itself. It happens a much longer time scale as compared to the orbital period. So for each point in the orbit, you can basically associate a binding energy for assuming a circular orbit, and that basically has the orbital energy. Basically, it has the kinetic energy of the reduced mass, and there's the gravitational potential energy. And because this is a bound system, you can relate the binding energy and the potential energy and the kinetic energy, and basically you can compute this basically the orbital energy as mu r square omega square, where mu is the reduced mass of the system, and r is the orbital separation, and omega is the orbital frequency. And so now, if you have a mass orbiting with a frequency omega, you can calculate the gravitational wave luminosity using the quadrupole formula. We kind of sketched it yesterday, but I also assume that you went through this in Mohanty's lectures last week. So this is basically, again, it's a large power of frequency as we saw yesterday. Yesterday I wrote it in terms of only the orbital separation only, but you can use, you can basically write all this omega in terms of r, or r in terms of omega because of the relation. So basically, that's adiabatic approximation. So now you basically assume that the energy loss of the system is entirely due to gravitational wave emission. And this is actually an accurate approximation as opposed to what we saw yesterday in the case of spinning neutron stars. There are much more dominant sources of radiation through electromagnetic radiation. But here, even if these, in the case of black hole, this is the only source of radiation as far as we know, gravitational radiation. But even in the case of neutrons, even if you put neutron stars with magnetic fields, etc., the amount of electromagnetic radiation is extremely negligible as compared to the luminosity of the gravitational waves. So this is a pretty good approximation in the case of these in-spiral and compact binaries. So you basically equate the rate of the change of the orbital energy to the energy flux of gravitational waves in an orbit average sense. So, and it is a good approximation because in the early in-spiral, you can treat these in-spiral orbit as an adiabatic perturbation of many, many circular orbits. And this gives you an ODE which you can solve. And basically you can solve this to get omega as a function of t, because this gives you dE by dt. So you can plug this in and it'll give you some d omega by dt, which you can solve. And once you got omega as a function of t, and then you can get the orbital separation also, and you can basically plug it in the formula that we wrote down yesterday, which basically has this ratio of these two time scales. This is the gravitational radius of the reduced mass divided by the distance, gravitational radius of the total mass divided by the orbital separation, which is basically the compactness. So with time, basically the compactness, which is gm by c square r, increases, and that is causing basically the amplitude to increase. And it will also have an imprint on the evolution of the frequency through this energy balance equation. So both the the orbital separation reduces and the orbital frequency increases through this relation. So you can calculate. So this is just using this leading order calculation, the quadrupolar formula. One can calculate the gravitational waveform, and that looks like these chirping signals. This shows how, using the leading order calculation, what is the expected gravitational wave signal from a binary black hole system with a mass of about 30 solar mass, which is the kind of system that we just discovered for the first time using LIGO/Virgo, at a distance of about 100 megaparsec, starting from about a gravitational wave frequency of about 15 hertz, which is what we are observing now. So we would see a few tens of these cycles of this gravitational wave before these approximation becomes inaccurate, and basically it just blows up. So one has to do something else. So while this provides a good approximation to the gravitational waveform and in spiral rate at very early times, for example, in the case of the Hulse-Taylor binary system, the observed change in the orbital period agrees quite precisely with just this leading order calculation. But if you go to a slightly more relativistic system, like the double pulsar, you also see several higher order effects. There are several post-Newtonian effects that one could measure from these more relativistic system. And basically, there is a systematic way of computing these signals using this post-Newtonian expansion, which basically involves an expansion of the relevant quantities in terms of a small velocity parameter. It is a gauge invariant parameter, which it basically defines in terms of the gravitational wave frequency, which is in the leading order is twice the orbital frequency. So you can see that this is gm by c cube has dimensions of time, and omega has dimensions of frequency. So this is a dimensionless parameter. So it has a maximum value of 1 and typically much less than 1. So instead of writing these equations in terms of omega and r, one could re-express this in terms of these gauge invariant parameter, dimensionless parameter, and then that gives you basically just by writing this one, you can write as dE by dV times dV by dt, and that give you an expression, an ODE for the time evolution of this velocity parameter. So it is related to the gravitational wave flux and how the orbital energy changes as a function of the derivative of the orbital energy with respect to the v. Now, we also want to compute the phase of this gravitational wave signal, and that is basically using the definition of the orbital frequency as the time derivative of the orbital phase. And using this, you can relate this right in terms of this velocity parameter v. So to compute the gravitational wave phase, which one could use to compute the gravitational waveform, one basically solves these ODEs, the set of ODEs. And so far, we have computed the gravitational wave luminosity using the quadrupolar formula, which is the leading order gravitational wave flux. And the binding energy was just a Newtonian binding energy, or the orbital energy. And in the last few decades, people like Bala, who will speak now next after this one, have computed this systematically higher order post-Newtonian expansions of these gravitational wave flux and the orbital energy, and this is known to several higher orders in the post-Newtonian expansion. So something like v to the power 9 is something that we know now. So it's a very tedious calculation, and all these terms have been computed to very high order. And one could plug in these ones in these set of ODEs and solve. And there are certain freedom in how to solve this also that will result in different kinds of approximations in producing the waveforms also, even after starting with the same post-Newtonian inputs. So there are some ambiguities of what is the right waveform, etc. I'll discuss a little bit of that as we proceed. But there is a way of doing it. So that will give you basically the phase of the orbit or the phase of the gravitational wave as a function of this post-Newtonian parameters. Now, you could also have other kinds of effects. So far we have been treating these as just point particles moving their gravitational interaction. But if these point particles also have a spin angular momentum, they are black hole spin angular momentum, they would drag the initial frames around this, which can couple to the space-time of the companion object. And there is a spin-spin interaction and a spin-orbit interaction because of the spin angular momentum of these objects. But again, during the early times, okay, so this dragging of initial frames can cause a precession of these spins. For example, this spin of this object can basically can couple to the spin of the companion object as well as the orbit, which will cause the spins to precess around some total angular momentum axis, the J here. And again, to conserve the total angular momentum J, the orbit also has to precess in the opposite direction. So there is a certain time scale associated with this precession also. But during the early in-spiral, there is a convenient separation of these time scales, which again allows us to do some amount of averaging. So of course, the orbital time scale is the fastest. The next, and which is actually much shorter than the time scale of the precession of the spins and the orbital angular momentum, which in turn is much faster than the time scale in which the orbit shrinks to the radiation reaction. There is this separation of time scales, and that simplifies this problem. So for example, just like we could associate an instantaneous orbital energy to each inspiraling part of this inspiraling orbit and compute these energy balance. During the precession timescales, one could neglect the fact that you have an inspiraling orbit here also. So you can think of this as an orbital average quantity. So this is so basically you can write a equation to ODE to write that describes the precession of the spin vectors. The SI are the spin vectors, S1 and S2, and which is basically a cross product of a particular vector frequency called precession frequency with the spins itself. And you can see that because the cross product, if the spins are actually, okay, this precession frequency is in the direction of the orbital angular momentum, the vector. And if these spins are actually aligned or anti-aligned with the orbital angular momentum, then there is no precession. They stay as aligned or anti-aligned. And this is the kind of scenario that you would typically expect in the case of an isolated binary evolution, where there is, because the angular momentum exchange, that would align the spins of these black holes with the orbit. But on the other hand, if you have objects that also have some misalignment of the spins with respect to the angular momentum, then this would cause the precession of these spins. And again, the timescales of this timescales much shorter than the in-spiral timescales. The total angular momentum also has to conserve. This means that the orbital angular momentum has to precess in the opposite direction. So dl by dt is basically equal to the negative of the ds1 by dt plus ds2 by dt. Then this will give you a set of additional equations to solve when you have spins also involved. So this is the same equation that I wrote that will describe the in spiral of 2-point particles. But now, if you also have these two spin vectors, they'll give you 3 equations for the spin evolution of the first object and second object, and again 3 equations to describe the precession of the orbital angular momentum. And so this, it is sort of a cartoon of how this would happen. So there's a time goes in this way. So these individual spins would precess, and the orbit also has to precess so as to cancel the total angular momentum. So you would see that a fixed observer from space would see that orbital plane precessing during some intermediate time scales. And this has a non-trivial imprint in the observed gravitational waves, because the gravitational waves are primarily beamed along the direction of the orbital angular momentum. So, and because of the orbital angular momentum direction is changing, these gravitational waves are beamed towards different directions during this time scale of precession. And a fixed observer in space would see modulations in the observed, in the amplitude as well as frequency of the observed gravitational wave signal. And here is a calculation of how one example gravitational wave signals would get modulated because of the precession of the orbit. So in the absence of this orbital precession, you would have seen this normal chirping signal that we saw earlier, where both the amplitude and the frequency is increasing with time. But the precession basically introduces an envelope in the amplitude, as well as there is a frequency modulation also, which you would see if you look close. And the fact that the time scales of this orbital precession, so the precession is longer, is also obvious on this one. The time scale for the orbital motion is this short period, but time scale for the orbital precession is much longer. But eventually, all these separation of time scales become blurred at the late part, so you have all these approximations have to break down when these objects come very close. Finally, so you can write down this phase of the observed gravitational wave signal or the orbital frequency as a post-Newtonian expansion, and one could identify that different physical effects contributing to different post-Newtonian orders. So the leading order is given by the quadrupolar formula and the Newtonian energy, and there is the first Pn order, which is what you expect, what you see from Mercury's, for example, in the case of eccentric orbits. This is basically the same precession of the Mercury that we have seen in the Mercury's orbit. Then you see again the fun point 5 Pn correction, the spin orbit coupling, the 2 Pn correction, the spin coupling, etc., etc. And we had a question yesterday about what would happen for the case of neutron stars, because at some point the fact that they have a finite size and object, and they also have their own binding energy, will also contribute to the signal, and this would affect both the orbital energy of the system as well as the amount of gravitational waves. So they would both add a correction to the post-Newtonian correction to both the gravitational wave flux at some high order, 5 Pn order, and the orbital energy also at a large order. I forget, it's 6 Pn or I think it's 6 Pn. No, it's also 5 Pn. And if you solve this to compute the phi of phi, it would also add a 5 Pn correction to the gravitational wave phase. I forgot to tell you that the convention of ordering the system by convention, the v to the power of 2 is called 1 Pn, and v to the power 4 is called 2 Pn, etc. So, for example, order v is called half Pn, and order v to the 3 is called 1.5 Pn, etc. It's historical reasons. So 5 Pn correction means order v to the 10 correction to various quantities, the leading order. So these finite size effects would come at v to the 10 or 5 pn. And again, in this adiabatic approximation, you can treat these finite size effects in terms of a single scalar quantity for one object, and this is called tidal deformability, which is basically, it is a ratio of the induced quadrupole moment of an object by a given tidal field tensor. So here is a cartoon picture. This is a cross-section of two neutron stars when they are very close in their orbital separation. So while the neutron stars were originally spherical shape, because of the tidal interaction, they would get deformed depending on their nuclear equation of state, how soft or stiff this equation of state is. And in the adiabatic approximation, this is treated in terms of a single quantity called the tidal deformability. And these v to the 10 terms would depend on the tidal deformability of the two objects. And because even if you have the same equation of state, depending on if these have different masses, they would have different values for these lambda parameters. And we have some constraints of these tidal parameters from the observation of this first double neutron star system, which has helped to rule out certain equations of state models, etc. I will tell a little bit of that in the later part. So that's sort of a schematic of how you can identify these various physical effects in the observed gravitational wave signal, which will give us some hint on how to measure these things also. But unfortunately, as you can see, these are all these 1 pn, 5 pn, etc. are just described by the just the combination of the two masses, which are point particles in this model. And you can see that basically there is a lot of degeneracies between different effects, because the 2 pn, sorry, the 1.5 pn is a combination of the spin effects as well as the mass ratio of the system. So the spin effects it's rather hard to measure the individual spin angular momenta of these two black holes, because they are highly degenerate with the mass ratio of these objects. So in the leading order, it turns out that the spin effect can be approximately modeled by a particular combination of the projection of the spins onto the angular momentum. So these are S1 and S2 are the two spin vectors, and the L is the angular momentum. So the dot is a dot product. So you can see this is basically a particular combination of these projection of these individual spin vectors to the angular momentum. In some sense, this is called the effective spin parameter. In fact, this is the best measured combination of the spins and the angular momentum that we can measure from these observed signals. And you could see that most of these observing papers would quote these value of this effective spin parameter and its posterior, etc. So eventually, as this binary in spirals, this post-Newtonian approximation breaks down. There are two effects that is breaking down. One is that your adiabatic approximation itself breaks down, because the in-spiral timescales becomes comparable to the timescale of the orbit. So you cannot treat them as adiabatic perturbations of circular orbits. That's one effect. And that is characterized by an adiabatic parameter, which is how the omega dot, the frequency is changing as compared to the frequency square itself. And it's a dimensionless parameter, and you can see that how it changes as the binary goes deeper and deeper into its potential. And at the same time, also the velocity also increases. So it doesn't become a small parameter. It also blows up, the expansion blows up. So at some point, these approximations break down, and we'll have to replace it with either better approximations using some resummation techniques, such as the effective one-body approach, I'll describe a little bit. And eventually, all these approximations break down, and we have to replace it with numerical relativity simulations to do exact solution of the Einstein's equations. So basically, yeah, this is so in the inner part of the orbit, basically you have to replace these post-Newtonian calculations by solving Einstein's equations exactly. It is a broad topic by itself, so I'm not going to go in detail, but broadly one write this in the Einstein's equations in terms of an initial value problem. So one chooses a gauge so that one can write a set of time evolution equations. You basically decompose the space-time into a 3+1 formalism. and you assign a time coordinate and spatial splices which are evolved in a time coordinate, and you start with some initial data and evolve them using some appropriate numerical schemes. And although this has a lot of history, but only about earlier part of this 21st century, this has become successful in 2005 or so. But now there are several numerical relativity codes that can evolve these binary black hole system over several tens of orbits and get very accurate models of the expected signals. And still, the solution of solving binary neutron stars is a harder problem because that involves, apart from GR, fluid dynamics, nuclear physics, and magnetic, MHD, microphysics, including neutrinos, etc. So that is a much harder problem. But again, there has been significant progress in the last 2 decades on this frontier. So we have pretty good accurate models of these expected signals describing both the latent spiral merger and the subsequent ring down of these compact objects. The final part, again, even in the earlier results from the numerical simulations, we had a lot of confidence in these simulations because we had something to compare against. So, it turns out that at early part of these numerical related waveforms agreed extremely well with the post-Newtonian calculations of the same system. And also, the later parts agreed quite well with calculations of the black hole perturbation theory. So, as I said earlier, the late part of these oscillations of this deformed curved black hole can be computed using black hole perturbation theory. And this shows, for example, an agreement between such calculations of this quasi-normal mode, shown in this red line, and the black line shows the late part of the in spiral and the merger ring down of a binary black hole system as computed by numerical relativity. So you can see that there is extremely good agreement between NR and quasi-normal mode calculation using black hole perturbation theory, which again gives a lot of confidence in these two calculations. So the theoretical models that are used to extract the physics from these observations, as well as theoretical models that are used to search for these signals in the data, are some way of combining all these multiple techniques to model the same problem. Because in principle, one just need numerical relativity. If you have infinite computing power, you could solve all these by using numerical methods. But these are very expensive. So in practice, one has to marry all these analytical and perturbative approaches with numerical relativity to get the best out of all of them. And one such quite elegant method is the so-called effective one-body approach, which basically takes inputs from post-Newtonian calculations and use some clever resummation techniques to improve their convergence. And basically, this effective one-body dynamics idea is something inspired from our standard treatment in the classical mechanics. You map the two-body dynamics into the dynamics of an effective dynamics of a one body in the presence of a deformed metric. So here is a cartoon version. You have a space-time that is described by that has two black holes in it, and one could find an approximate equivalent map in which is basically equivalent to the fact that you have the effective dynamics is described by the motion of a test particle in a deformed space-time. And these deformations can be calculated perturbatively, which is exact at a particular Pn order. But one could introduce some additional parameters, free parameters at higher post-Newtonian orders, and one could tune these parameters so that the final waveform is basically is fitted as a good agreement with the actual numerical relativity simulations. And this takes this binary into through the in spiral and the plunge, the merger part. And finally, one attaches a spectrum of quasi-normal modes to these in spiral plus plunge waveform to create a full waveform describing the entire in spiral merger and ring down of these objects. And it's a very successful and approach, and we use very widely in extracting the physics from the observations and to search for these signals.
Ajith, is the deformed metric, is it static or dynamic?
It is dynamic. It is dynamic.
So you update it.
Yeah.
From period.
There is a, so you write an effective potential, and you can write on a Hamiltonian for that, and there are the Hamiltonian equations that are evolved. So that is dynamic. Are there any questions? The second approach is more of a phenomenological approach, and here again one relies on the fact it's some way of cleverly interpolating numerical relativity waveforms across the parameter space. So here one relies on the fact that you have a set of numerical relativity waveforms that are starting from a wide enough orbit, and we can match these waveforms with a post-Newtonian waveform that are accurate at that separations. So here is this shows here these black dashed line shows a post-Newtonian waveform, approximate waveform, and so it starts from it can start from minus infinity and going up to some separation just close to the merger, while these red waveform is a numerical relativity simulation, which starts when you have some finite separations. So there is some junk radiation. After that, there is a beautiful agreement between the numerical relativity and the post-Newtonian calculations. Eventually, you can see the post-Newtonian approximation becomes inaccurate. They start to diverge. And you can create some sort of a hybrid waveform that combine these Pn as well as numerical relativity to create a full waveform. And you can do this at different points in the parameter space, like in the space of mass ratio and the spins, etc., because the waveform would look different for different choices of these parameters. Then one can try to parameterize these hybrid waveforms in terms of suitable analytical functions. And the obvious thing to do is that we know that in the early in spiral, the post-Newtonian approximations works extremely well. And you can try to, especially with this, using some resummation techniques, one could improve the convergence of these approximations. And one could introduce again some higher order effective post-Newtonian terms and tune them against numerical relativity, and again match with some quasi-normal modes to model the final ring down. And one writes down a set of analytical expressions in the frequency domain, which are appropriate fitting functions to describe these exact waveforms. So these are also very used widely. They are extremely fast to evaluate. They have a lot of value in the data analysis part. Recently, the fact that you have more and more efficient numerical simulations, and a large number of them also have prompted people to directly use these simulations across, instead of trying to find appropriate analytical methods to model these things. And one is the so-called numerical relativity, surrogate waveforms. And the idea is that you have if you have a large enough number of waveforms densely covering the parameter space, you can find an appropriate orthonormal basis to describe these waveforms and use them as an interpolants, so that one could evaluate these waveforms anywhere in between where you have in this interpolation. So you can interpolate, you can find appropriate interpolation functions to evaluate these waveforms at any arbitrary points in the parameter space, and use them for such as in parameter estimation, etc. So one advantage is that one basically shortcuts the whole analytical modeling that is hard, and it introduces some error by itself. But the disadvantage is that it requires a large number of numerical simulations to do this orthogonalization of to find it in the basis to do this interpolation. But these are also being used in the gravitational wave data analysis now. So that sort of summarizes my quick survey of the modeling part of the expected gravitational wave signals from compact Barn arrays. And the next 20 minutes or so, I will give a summary of what we have learned about these sources from the observation of gravitational waves over the last decade. But maybe I could pause for a minute to ask if there are any questions on this part. Okay, I will go ahead. So in the last decade, since 2015, LIGO and Virgo have conducted 3 observing runs, and the 4th one is going on. And we have observed hundreds of gravitational waves already. The number has crossed about 250 so far. And the last 150 is from the 4th observing run that is ongoing. And this shows like a cartoon, a schematic picture of the masses of these black holes and neutron stars discovered by gravitational wave observations during the first 3 observing runs of LIGO. So all these blue dots shows the masses of the black holes. So one cluster corresponds to one signal. You are starting with 2 masses, and they would merge to form a more massive black hole. So that is shown by this cluster. And these orange dots shows the neutron stars measured by gravitational observations. And you could see some objects which are colored half in blue and half in orange. We are not exactly sure whether these are some heavy neutron stars or extremely light black holes. These are some puzzles that one is dealing with these days. You can already see that they are opening up, in some there are new populations of objects that we have not seen before. These crimson dots are the black hole candidates discovered by X-ray observations from our own galaxy. And you can see that on average, the LIGO Virgo black holes are much more massive than the black hole that we see from our own galaxy. On the other hand, these yellow dots are the neutron stars measured from binary pulsars, and they're not very different. But there are some questions of what is the maximum mass of a neutron star, because depending on that, one could classify these objects either as black holes or neutron stars. In either way, this is a puzzle because traditionally these objects are they are lying in a region of so-called mass gap region between about 3 solar mass and 5 solar mass, where people believe that there won't be any black holes, and they are too light to have stellar mass black holes formed as a result of core collapse. And they're also too heavy to be neutron stars also. So one has to deal with this puzzle of these objects now, and it's not entirely clear what these are. And a huge amount of science have come out of these observations. These are, of course, the first observations of merging black holes and double black hole systems and black hole neutron star binaries. We have not seen these binaries before. Of course, we have seen binary systems of 2 neutron stars as binary pulsars in our galaxy, but the first time we are seeing them merging also. As I said earlier, most of the black hole candidates from our own galaxy have masses less than 10. So the conventional wisdom was that until then was most black holes in the most stellar mass black holes that are produced by the collapse of massive stars would be ordered at say 10 solar mass or so. But we are seeing a new population of black holes which are extragalactic, which are much more massive than the black holes that we see in our own galaxy. This is a bit of a puzzle, but it's not a very serious puzzle because depending on the metallicity of the progenitor stars, one could form a massive star at the end of the stellar evolution also. The issue of forming these heavy black holes is that a massive star would lose a large amount of its mass through stellar winds during its evolution. And the amount of wind loss depends on the metallicity in the star. So if you take the metallicity that is available of our galaxy, one would expect a much larger amount of wind loss, and the resulting black hole at the end of the collapse would be not very heavy. So that was a conventional expectation that most black holes would be an order 10 solar mass. But the early galaxies and et cetera, there could be different environments, and astrophysicists believe that it is not very difficult to produce these heavy black holes through the evolution of low metals massive stars. There is also one event that is giving a potential evidence of intermediate mass black holes, which are black holes more massive than about 100 solar mass, but less massive than the supermassive black hole that we see at the center of galaxies. This is a slightly indirect inference. The inference is that we have seen this extremely short signal, which is believed to be produced by the merger of two black holes, each weighing about 70 solar mass or so. And we only see the last part of the inspiral and the subsequent ring down of the remnant black hole. It's a very short signal, but one could still extract the properties of this source, assuming that this is a quasi-circular inspiral, and then one would get that, one would see that the remnant black hole is about 150 solar mass. But because of this very short signal, there are alternative models also explain these observed signal. People have produced, this could be direct collisions of instead of an inspiral orbit. People have argued that this could be in spiral, it could be an eccentric binary systems, all kinds of things. But there is a potential evidence of the remnant being an intermediate mass black hole of more than 150 solar mass. There was this particular remarkable observation of a binary neutron star merger. I will tell a little bit about that in the upcoming slides, where we have observed not only gravitational waves, but also the electromagnetic radiation across the spectrum of frequencies. And this has resulted in an enormous amount of science, both in our understanding of gravity. It shows a potential of doing cosmography using observations. There are some interesting implications in nuclear physics, and so on. There are these slightly weird objects that we don't exactly know. These could be either the heaviest neutron stars or the lightest black hole that we have ever seen. These are these mass cap objects. We also have seen binaries with large mass ratios, and they are rare astrophysically. But one interesting aspect of these large mass ratio binaries is that they would contain imprints of the higher multipoles of the gravitational radiation. So as we have seen, the quadrupolar radiation is just a leading order calculation of the gravitational waveform. The leading order gravitational wave radiation is quadrupolar, but there are higher order multipoles of the radiation also. And these higher order multipoles are excited when there are large asymmetries in the system. For example, where you have a large mass ratio, you see a significant power in the higher order multipoles of the radiation. And we have seen this in at least two signals we have, and basically they would introduce higher harmonics of the orbital frequency in the observed signal, and we clearly see these imprints in these two events. So let me go through a little bit of more details on the implications of these observations. One is that these observations have provided us a way of testing general relativity in the regime of extreme gravity and extreme velocities. Indeed, there has been a large number of a century-long history of testing GR in various astrophysical contexts and laboratory contexts. But most of these tests, if not all, are in the weak field regime of GR. And this, in the case of these merging binaries, just before the merger, these objects are moving with velocities close to the speed of light. So here is a plot showing how this post-Newtonian parameter changes the function of time. So it is going as close as 0.6 when these black holes are moving at just before merger. And the black hole separation is actually moving in units of they are coming to regions close to the orbit, to the gravitational radius itself. So you're seeing an extremely these black holes spiraling in an extremely strong gravity environment. So you would expect whatever deviations that one would anticipate from GR, you would see some imprint of that in the observed gravitational signal. But in the absence of any reliable predictions, it turns out that it's notoriously difficult for any alternative theories of GR to GR to make reliable predictions of the expected gravitational wave signals from these kind of systems. So in the absence of any such reliable predictions, one is doing some kind of a null kind of test. One is asking how well the data is consistent with GR itself. And this is done in multiple ways. So for example, one could, the least model dependent way would be you kind of subtract your best fit data, best fit signal from the data, and ask whether there is any power left in the residual. So it is the most model agnostic one could do. One could also kind of, since we know these post-Newtonian waveforms and we have these coefficients at various p and orders, which are unique functions of the properties of the object, like masses and spins, etc. One could introduce some deviation parameters that will, that also correspond to certain parameters in alternative theories and constrain the values of these parameters. And so far, all these parameters are consistent with 0. One could do some other kinds of consistency tests. For example, one could extract the parameters, like the black holes, masses, and spins from the early in spiral, and one could make a prediction of what would be the mass and the spin of the Ramanujan black hole. Because now you have numerical simulations that predict exactly the amount of energy and angular momentum lost into gravitational waves. So you could then go back and measure the properties of the final black hole from the quasi-normal modes of the Ramanujan and ask how well these two different estimates are consistent. There are several such consistency tests have been performed, and so far the data is, we don't see any evidence of deviation from GR in the data so far. This, yeah. No, yeah, sure, no, of course not, yes. No, the metric is far from, yeah, it's still far from being probing quantum scales, but the curvature scale is still kilometers. Among all the astrophysical tests, this is the most relativistic. So yeah, so for example, they are stellar mass black holes. So the curvature scales are tens of kilometers.
So it's extreme in the sense that it's a new record.
That's right. Yeah, yeah. And basically all the nonlinear effects of gravity would have manifestation, but still far from probing any quantum gravity. It's true. Yes. This one particular observation of this multi-messenger observation, where we have seen both the gamma rays as well as gravitational waves from this one binary neutron star merger almost at the same time, have put a very tight constraint on the speed of propagation of gravitational waves, which has already ruled out a number of alternative theories which are invoked in the context of cosmology and dark energy. But of course, the cosmologists are very clever and theorists, so they are also now modifying these theories to come back to the scenario also. But this has been quite useful in constraining a number of theories or the parameters of such theories invoked in the context of cosmology. They also have provided at least in principle demonstration that gravitation, these mergers, compact matter race mergers are standard candles and can be used to do cosmography. And here the idea is that you can directly measure the luminosity distance to the source using gravitational waves without relying on any distance ladders. And if you have an electromagnetic counterpart, that will also allow us to measure the cosmological redshift, which is impossible to measure from gravitational observations. So from this multi-messenger observation of this one neutron star merger, we have a posterior of the Hubble constant from the Hubble diagram. And it's currently very imprecise, it's very broad. And as compared to this is the green is the CMB measurement of the Planck, and the orange is the supernova measurement, slightly old now. But you see this clear difference between the so-called Hubble tension and this is the posterior of the Hubble constant from the gravitational waves. Currently, it's so imprecise that it covers the entire range, but one hopes that with future observations, one will be able to measure these things, combine these measurements and make a much more precise measurements and contribute to this ongoing discussion on the Hubble constant. I mentioned about that these finite size effects would add an imprint on higher order post-Newtonian correction to the observed waveform. And these are described in terms of these tidal deformability parameters, lambda. This is a posterior on the tidal deformation of the first object and the second object from the double neutron star merger that we observed. And you can see that basically they prefer, we don't have a non-zero measurement of the tidal deformation yet, but we have upper limits. For example, certain equations of state predict large values of these tidal deformation for the given tidal field. We do not observe such things. These are the stiff equations of state that predict fairly large neutron stars that get tidally deformed for a given tidal field. And we do not see any imprint of such tidal field, such tidal deformation in these observed gravitational wave signal, which has helped us to rule out some of these stiff equations of state. But there are many serious equations of state that are still consistent with the non-observation of the tidal deformation. In the future, once we have higher signal-to-noise ratio measurements, one hopes to measure a non-zero value for the tidal deformation, which will give us a lot of hints on the nuclear equation of state. Now that we have this order 100 gravitational wave signals, which are going to be a few hundred in the next year or so, one is starting to do population inference, basically making statements about what is the distribution of black hole masses in the universe, what is the distribution of their spin angular momenta, et cetera, et cetera. And this is a reconstructed distribution of the masses of the primary object in a binary black hole system. So you see this sort of roughly a power law distribution with some hint of some shape here. Excuse me. And this could be related to what I briefly mentioned yesterday about the possible existence of pair instability supernovae, which basically leaves no compact object at the end of the supernova. But this could very well be a statistical fluctuation also, because we don't have a large enough sample to make accurate reconstruction of these properties. So one has to wait for a few more years to see how this black hole mass function would change. One is also making some modest statement about the nature of the black hole spins. As I said, it's very hard for us to measure individual spin vectors accurately, precisely, because of the degeneracies. But one can measure a particular combination of the spin effects. It's called the effective spin parameter. And we see that, again, parts of surprise is that the spin seems to be not very large. They are close to zero, but there is some small hint of a small non-zero value. This is also a bit of a surprise because there has been spin measurements from the galactic black holes through X-ray observations, etc. And most of them predicts extremely high spins for these black holes. So the fact that the LIGO-Virgo black holes are very modestly spinning was again a surprise. One is also measuring another combination of spins which describe the precession effects, which is called chi-p. Again, we see a small hint of a small non-zero value in the population. But these things, again, one has to rely on more observations to see how well they stand the test of time. One is also able to see how the distribution of the mergers across the cosmological redshift is. So far, we are measuring only the low redshift range. It's the merger rate per co-moving volume as a function of cosmological redshift. We are currently measuring only at this low redshift region, about less than 0.5 or so. But then, if you have some parametric model of how the binary mergers are distributed across the redshift, one can try to constrain the parameters of that model and make some predictions of how the mergers would evolve at higher redshifts also. So now, in the next few years, you'll be probing higher and higher redshifts, and we'll be having a more accurate understanding of how the mergers are distributed across cosmic time. We are also making some modest contributions to cosmology. Also, we are having this great lecture on primordial black holes yesterday, and there was discussion about how the constraints from various observations are helping us to rule out this possibility or allow this possibility. The gravitational wave observations are also making some modest constraints on the abundance of primordial black holes, especially the possibility of them being dark matter. And one is that if there are subsolar mass black holes, which are 0.1 solar mass to about 1 solar mass, if they can form binaries, one could search for them. And the known observation of such binaries could be used to put some constraints on the abundance of such, on what fraction of such subsolar mass black holes could be dark matter. And currently, this constraint that they can't be 90%, they are like 10% or something. Similarly, such primordial black holes with masses of 100 solar mass to a few thousand solar mass, if they exist, they could also introduce microlensing effects on the gravitational waves, just like the microlensing effect on light produced by smaller mass black holes, which we heard yesterday, constrained by Subaru, etc. And it's a very similar effect, but that's different also. Here, the gravitational waves are sensitive to primordial black holes of much higher masses, a few hundred solar mass to a few thousand solar mass. And here also the lensing effects are also much more unique, because here the gravitational radius of these black holes are comparable to the wavelength of the gravitational radiation. So this lensing happens purely in the wave optics, while in the case of light, everything is geometric optics. So you see some very characteristic deformation of the observed gravitational wave signals if they are lensed by such primordial black holes, and a non-observation of such signatures in the observed gravitational waves can be used to put some constraints on the fraction of dark matter in the form of such primordial black holes. Currently, these constraints are very modest, but they are going to improve even in the next year, maybe going to 0.1 or so. So with future observations, this will be a new way of probing such primordial black holes. I briefly mentioned about these multi-messenger observations of a double neutron star merger. This has brought in a huge amount of science. I don't have the time or expertise also to cover the entire science, but some of the most important astrophysical implications are that we have the first evidence that the short GRBs are powered by mergers of double neutron stars. This has been hypothesized in the past, but it's the first time we are seeing a direct evidence of that because of the short GRB that is directly after these observed in spiral of two neutron stars. We also have, astronomers have looked at the isotropic emission, thermal emission from the so-called kilonova produced by the merger, and have seen the hints of production of heavy elements in this kilonova spectrum. And again, this has been hypothesized in the last decades that a good fraction of the heavy elements could be produced in the neutron star mergers, and the observed light curves and spectra are consistent with theoretical models, or where these heavy elements are synthesized through our process in the merger ejecta. So I will stop in the next two slides or so, and I just want to kind of stress that these are really the first steps in this new branch of astronomy. The gravitational observations have only begun. With even modest improvement in sensitivity, the number of events that we would observe would dramatically increase, because even a factor of 2 improvement in sensitivity detectors would give you a factor of 8 in the volume range, and it would dramatically give you an order of magnitude increase in the number of events that we'd observe. That's why we saw 3 events in the first observing run, about 10 events in the second observing run, about 100 events in the third observing run, and we are only seeing a few hundred events in the ongoing observing run. So these number of events are increasing quite rapidly. New detectors in Japan and in India would join this network in the next decade or so, and this would significantly improve the science capability of this network, because we require a network of detectors to localize these objects in the sky, which we cannot do using single detectors. And there are also ongoing plans to upgrade these detectors, in particular in the US one, using the existing facilities. And they call the name of A Sharp, Voyager, etc., etc. And there are also ongoing proposals to build the next generation of gravitational detectors, primarily in the US and Europe, called Cosmic Explorer in the US and Einstein Telescope in Europe. So they will be having a factor of 10 improvement in sensitivity. They'll be observing millions of mergers during their operation time. So, and this will allow us to ask a number of very interesting questions. What is how do these black hole boundaries form? What is the black hole mass function? Are they primordial black holes or astrophysical black holes? One could make some precise probes of strong gravity. Can we find evidence of black hole horizon or the lack of black hole horizon? Are these black holes indeed, or they are something more exotic? and one could potentially see an imprint of such things in the observed gravitational signals. Both the tidal deformation measurements as well as the measurement of a post-merger signal from a double neutron star merger would contain important information of the nuclear equation of state at extreme density, which one cannot probe in the laboratories. So that's an important contribution to nuclear science also. These standard sirens, the compact binaries being a standard siren would give you a totally new way of measuring the cosmic expansion rate. We believe that the systematics of these gravitational observations are much better understood because they are much simpler phenomena as compared to, for example, type 1a supernovae. So they would have an important role to play to resolve this ongoing tension between different cosmological measurements. Apart from these are all from some sort of a guaranteed sources, which are, they exist. Apart from these known signals that we know they exist, one could see potentially new phenomena also. I broadly mentioned this yesterday. Other kinds of sources, the detection of stochastic astrophysical background is almost guaranteed in the next 10 years. One could see things like lensing of gravitational waves. Depending on the ellipticity, one could see spinning neutron stars in our galaxy and galactic supernovae. And one cannot rule out the possibility of seeing some unknown sources as well. So let me, I'll skip these slides in the interest of time. There is the LIGO India, which is something of very great interest to our Indian community in particular, but also the international community also has a lot of value because it basically adds a new node to the international network of detectors, which would significantly improve the ability to localize the sources in the sky. Okay, but I'm fine. Yes. So, and it's ongoing. Of course, it's a challenging project, especially in our Indian context. We are the first time we are doing a large project of its size in fundamental physics. So it has, one has to overcome a lot of infrastructure as well as systemic problems. But it is a great opportunity also. It is progressing. So this is some of the photographs from at various sites. This is led by 3 institutions. So one is the Center for Advanced Technology in Indore, which is basically has now, this is a staging station for the optics that would come from LIGO US, and where they are setting up a prototype interferometer and an optical facility to polish mirrors, etc. It's happening. This is a picture from the Institute of Plasma Research, which is developing the vacuum system for LIGO India. And this is a prototype vacuum system which has passed all the engineering tests so far. And this is a computing facility at IUCA, which is coordinating a lot of the human resource development activity. And this is a CAD drawing of the site, how the site would look like in the next decade or so. And currently, we have already started the project has started some construction. There's a site facility, etc. And they're hoping to roll out the large-scale construction the next year or so. There are, as I said, there are ongoing proposals to build the next generation of ground-based gravitational detectors. They are primarily driven by US and Europe, and this is a concept image of the Cosmic Explorer in the US. It's like a large LIGO, just 10 times bigger than LIGO, surface detector. And the Einstein telescope, it is likely to be an underground detector. They are still debating on the precise configuration and the location of these detectors. It could be a triangular underground detector, or it could be L detectors at multiple places also. But in any case, these would have sensitivities at a factor of 10 better than the current instruments, which will basically enable these observatories to detect binary black hole mergers basically out to the entire history of cosmos where we expect these binaries would have formed. So they could hit redshift as large as 100 and certainly at tens. So they would be observing practically all binary black hole mergers in the universe during their operation time, with a small loss at low masses. So it would result in a huge amount of new science. And if you're interested, there is this nice science book which is compiled by the international community, which summarizes the main scientific contributions that one would expect from these next generation instruments. So let me stop here, and following yesterday, we saw that the coalescing boundaries of black holes and neutron stars are the most promising sources of gravitational waves. This is consistent with our previous expectation. There were multiple reasons to believe that, and it is vindicated by nature. They are simple systems, well described by GR, and which allows us to use optimal techniques to search for them, as well as to extract the source properties very reliably, which gives a lot of confidence on using them to test GR, understand cosmology, nuclear physics, etc. And it's undoubtedly, the gravitational observations have opened up a new branch of astronomy. We have made the modest steps, but it would go to significant new discoveries in the next couple of decades. So thank you very much. That's all.
Thank you very much, Ajith, for this fantastic set of 2 lectures. So yeah, please.
Thank you for the nice talk. So can you just repeat the distribution of the spin is for all of the observed binaries?
That's right. Yes, yes.
Okay.
It's a distribution of spins of black holes in binaries.
In binaries,
it doesn't
yes.
mean that all the black holes would have the same spin.
So this is all of them.
Yeah.
Yeah.
Yes, yeah.
And okay, thanks.
Well,
And,
this is like instead of a population property.
the
That's right.
population,
Yes,
yeah, at the
yes,
moment, yeah. Okay. And so is there any constraints that people are doing at LIGO about magnetically charged black holes?
Magnetically charged black holes. It turns out that, at least from simple estimates, even the black holes are highly magnetized. Their effect on the gravitational wave signal is going to be very weak. I don't think that there are haven't seen any recent papers on that, but the rough order of magnitude calculations suggest that it's very difficult to see an imprint of magnetic fields on the gravitational waves, because their energy is still very small as compared to the gravitational energy.
Okay. And are there any constraints on the memory effect that we have heard about a lot?
So far, none, because it's very hard to measure, as you know. But there are papers that claim that by stacking a number of observations, etc., one might be able to see a ramping up of memory once we have a large enough number of observations, but none so far.
Thank you.
Okay, Thomas?
Yeah, sorry, perhaps probably you said it, but I missed it. You mentioned these 2 candidates, which are neutron star and neutron star black hole, which had no electromagnetic counterpart. Yes. I mean, I guess for the neutron star black hole, you wouldn't expect one necessarily?
Yeah, so it depends on the mass ratio. Again, the conventional wisdom is that if the neutron star is the black hole is light, you have that they are comparable masses. They have a larger tidal effect, so then we have a tidal disruption of the neutron star, and you have an unbound ejecta. And the expectation is that this would happen only if the mass ratio is less than 5 or something, 5, 6, depending on the spins. But so if you have a high mass ratio object, if you have a large black hole and small neutron star, you don't expect typically electromagnetic counterpart. But if they are comparable masses, you would expect electromagnetic counterpart.
Okay. And why wasn't anything seen for the neutron star?
Not entirely clear, but these are all, they were much farther away as compared to the double neutron star system. So even when you have a kilonova, etc., the luminosity would not have been very high. So plus they were not localized extremely well. So the electromagnetic telescopes could have missed some of these things also.
So there was no Fermi candidate?
No, there are no convincing candidates for these electromagnetic candidates.
Thanks.
So regarding primordial black holes, another thing to look out for would be the following, that if they are part of dark matter, they would be not in the galactic plane, but in the halos. So if you look at distribution of events, they may be separated for nearby events.
Yeah, but our probes are so cosmological that they are precise distribution of, these black holes that I talked about, they are not galactic. So their precise distribution in the galaxy is hardly going to make any difference in our statistics.
But in the local neighborhood of...
that cross-section is very small. The optical depth is very small. So your lensing you're talking about lensing effect, I believe, right? Yes. So lensing optical depth peaks somewhere in between the source and the observer. So you're still talking about extragalactic primordial black holes.
Yeah, hi, really great talk. So my question is, people are now recently computing nonlinear quasi-normal modes. So is there an understanding whether the ring down starts dominating over the margin? So was there a debate or?
Yeah, there is a lot of debate, and I'm pretty sure you know more than that. But so the answer is there is no consensus yet. There are some groups. So the question is, I don't know.
So what triggered this? That's the question.
So there was some hope that, right, there's a lot of hope that if you observe a late part of this merger with sufficient signal-to-noise ratio, one could fit this ring down with a spectrum of quasi-normal modes, and one could basically constrain properties independently and test no-hair theorem, etc. One still hopes that it is possible to do that. But it turns out that the current observations have only modest signal-to-noise ratio, right? So if you just look at really a late part of ring down, there was not enough information to extract these properties independently. So then people got a bit greedy and tried to see what best one could get from the given data. And the idea that you could maybe use the entire ring down, the post-merger signal, but then it is clear that one cannot fit in a usual quasi-normal mode. Then a group claimed that if you add several overtones of the quasi-normal modes, then you could fit the entire ring down signal part. But then the question is just a pure fitting, or is it related to the underlying physics? It's not clear. There is an ongoing debate, and in my opinion, it's not settled.
So I have a question regarding neutron star equation of state. So there are some ideas which says that when the neutron stars formed out of these supernova explosions, so it can contain some dark matter inside the neutron stars. It sometimes comes dark matter admixed neutron star. So my question is, with the data and upcoming data, so can we distinguish between dark matter admixed neutron star and just a pure neutron star?
Yeah,
is there any way?
It's an exciting possibility, and there is a lot of active research. Some of our colleagues are also here trying to look at these things. So in principle, yes. So what are the kind of possible effects one could see? Right? If a neutron star has a dark matter interior, it would change the equation of state, and it could change things like tidal deformation, etc. And one could see potentially a possibility of constraining these models in the future. Another possibility is that during these neutron star being trapped, dark matter particles getting trapped,
Captured,
and if it
yes.
probes and it transmutes to a black hole, then again that micro collapse could produce a burst of gravitational waves depending on how asymmetrically it happens. One could potentially look for these effects and constrain these possibilities. Yeah, sort of one more thing. So again, one more thing. You can ask, for example, again, we see a extremely light black hole, like one solar mass black hole, yes, with no tidal deformation. It's a potential evidence of either a primordial black hole or a transported neutron star, etc. So there are all kinds of these ideas are being proposed, but it's a bit too early to see such ideas putting into practice. And
so you are saying the uncertainty on the baryonic part is till now very large to comment on these things?
There are both. There are, there's a very open problem in the theoretical model side itself. There is a lot of free parameters, but also from the measurement point itself, we haven't observed yet loud enough signals so that we can make very precise measurements of the tidal deformation, other properties, etc.
I see.
So in the future, that hopefully would happen, because even the kind of signal that we see now, with future observations, you would observe with much higher signal-to-noise ratio, which will allow us to measure the tidal deformation much more accurately. Now, can you interpret these observations in a unique way? Something where
that's another story.
Yeah.
Thanks a lot.
Where does the PN approximation breaks down?
Okay, that's also a question of your accuracy, right? It doesn't happen, okay, it happens suddenly, it absolutely breaks down at some point, it blows up, but it also becomes slowly inaccurate, right? So the question is, it depends on how accurately do you require the waveform to be modeled. So this, for example, shows, right, it really stops here, this black dot here, but even well before a few orbits, it starts to dephase. Right? So what kind of dephasing can you tolerate? It depends on what is the science that you're trying to do. Perhaps just for detection, it might be okay to do some, you can allow some deformation because it might dephasing because you see the effective template to detect signals, but if you're making statements about astrophysics, fundamental physics, you want a higher accuracy. So it depends a lot on what is the purpose.
Okay, so you have something?
So we can definitely take this question outside, but I'm just curious, how long do you think LIGO India is going to take?
LIGO India?
Yes, and as I said, we can move this out.
Yeah, so the optimistic schedule is something like 6 years in the starting of construction. But we are really exploring new territories in terms of implementing and running a large project of this size in India. The uncertainties cannot be understated also. Optimistically, 6 years is something like the start of construction.
Okay, so I think let's close the session with thanks to Ajith. Thank you very much. And